full now with the attendees, so let's wait for 1 more minute.
Zet hem dadelijk al wat harder. Goed. Ja. Ja.
Yeah, perfect. So, hello and welcome everyone to our today's EFRC webinar, which is about flow meter errors and pulsating flows. My name is Tim Norden. I'm with Neumann and Esser, and I'm the chairman of the EFRC Standardization Group, in which this webinar and also the corresponding guideline was developed. With me today are Leonard van Lier, who is the pulsation and vibration consultant at TNO in the Netherlands, and also Andre Eijk, who's working now as the independent specialist and as the EFRC supporting members. And they are both experts in the field of pulsation and vibrations and will guide us today through this webinar. Before we start with the content, let's have a short look at the disclaimer, because legal things are always quite important. So I will just quickly read it. So the information in this presentation is brought to you only as guidance, and while everyone reasonable care has been taken to ensure the accuracy of its contents, the EFRC cannot accept any responsibility for any action taken or not taken based on the provided information in this presentation. So the EFRC shall not be responsible to any person for any loss or damage which may arise from the use of any of the information contained in any part of this presentation. The above disclaimer is not intended to restrict or exclude the liability for death or personal injury caused by own carelessness. After that, let's have a short look at the agenda. So what this webinar is about for today. So first, I will give a short introduction to the EFRC and to the webinar. Then Leonard will take over and give you an overview about the pulsations caused by reciprocating compressors and the summary of flow disturbing phenomena. And after that, Andre will talk about flow metering error discussions for the selected flow meter types, which are DP meters, Coriolis meters, and also ultrasonic meters. And we will end this presentation with the conclusion, of course, and some closing remarks. And at the end, we will also have a question and answer session. You are very welcome to put your questions here in the chat. And in the Q&A session, we will try to answer them all. If that's not possible due to time, for example, we will address them later via mail or by text. But be sure all your questions will be answered. So let's come to the introduction of the EFRC. The EFRC, as you may know, is the European Forum for Reciprocating Compressors. And we have a mission, and our mission is that we want to connect professionals to promote the reciprocating compressor on the path to a carbon-neutral world. This we are doing now with more than 40 members. We were founded in 1999 with 8 members, and now we have more than 40 members. And we have a main focus on the member experience, on innovation, of course, on cooperation between the members, and also of internal and external knowledge generation. And how do we do this? So we are carrying out R&D projects. We have the standardization projects, for example, as this webinar here, and also the guideline which is connected to this webinar. We are writing white papers, industry standards and guidelines. Then there's a student workshop. Every second year, we also offer trainings. And of course, you also know that there is every second year the EFRC conference. If you want to find out more about the EFRC, or even better, if you want to become a member of the EFRC, please visit the website or follow the QR code here, and you get a lot of more information and also the contact data. But of course, you can also contact one of us if you have any further questions to the EFRC. Okay, then let's go to the main topic. So to this webinar, I will give you a very short introduction. It's about flow meters and the errors caused by pulsating flows. Of course, we all know that flow meters are used for the process control and also for the custody transfer. And if we have an error in our flow meter, so if we have wrong measurements, then we may have some problems with the process stability, which also can lead to dangerous situations. Or, of course, we can also have negative economic consequences, especially when it is a custody transfer meter. Most relevant systems causing this effect are positive displacement machineries like reciprocating compressors, pumps, screw compressors, roots blowers, vane types compressors, and more. And in our standardization group, we recognize that there's quite a lack of knowledge on this subject. So there's a lot about flow meters and flow meter errors, but not about errors caused by pulsating flows. And therefore, we decided to develop this guideline. So this guideline is called Flow Meter Error in Pulsation Flow for Reciprocating Compressor System, which can be easily used, and you can easily check your system if it's prone for flow meter errors. Of course, this guideline, as we as the European Forum for Reciprocating Compressors, was specifically developed for positive displacement machineries with a focus on recips, but can also, of course, used for other systems with pulsating flows. And we highly recommend to use this guideline during the selection of the flow meter in a very early stage of your project to avoid any bad things happening at a late stage. And in this webinar, we will talk about 3 selected flow meter types. So this is, as I mentioned before, DP meter, ultrasonic meter, and the Coriolis meter. And now I would give the word to Leonard.
Yes, thank you, Tim. Can you hear me? Tim, maybe you can confirm that
Yes.
my audio is okay? Okay, good. Well, good afternoon. Happy to share some of my experiences on the topic of pulsations caused by reciprocating compressors. First of all, I would like to say that a reciprocating compressor is a very robust type of machinery, which has been deployed in industry for decades or even centuries. But it is also a pulsation machine. It's an intrinsic feature of the machine and the design that it gives unsteady flow. So these pulsation effects cannot be avoided, but with a careful design, you can mitigate the effects of pulsations. And it can be various effects. Today we talk about the impact on flow meters, but in general, we can mitigate these. And to our aid, there are very robust industry standards, mature standards, for example, the API 618 or 688 standards to help us how you should do a pulsation design and control the effects of pulsations. Simulation tools are available to study the effect of pulsations and vibrations in great detail. And there is a large experience, a decade-long experience with the application of mitigation techniques. So that's how we deal with it. The pulsation comes from the heart of the compressor, which you can see in the animation on the right. You see in the cylinder, the moving piston and the compression which takes place in the working chambers on either side of the piston cause a pulsating flow in combination with the action of the compressor valves. And you can see that illustrated in a bit more in this animation here, where you see the piston movement, but also the opening and closing of suction and discharge valves. The animation is a bit tricky, and that's why I always like to show it, because it suggests that pulsation effects only occur at the discharge side, at the outlet of the cylinder, but that's not true. Also at the inlet of the cylinder, the flow is unsteady due to this reciprocating movement. So pulsations are generated both at the inlet and at the outlet of the compressor. And in the picture on the left, you can see typically what happens during one revolution of the crank. So one stroke, you see 2 pulses on the discharge side associated with the crank end side and the head end side. And also on the inlet, you see 2 pulses. The shapes are different, but clearly you can see 2 pulsation effects per revolution. So to describe the source, that is determined by the design of the cylinder. It's dictated by the operating conditions, and it's also influenced by the capacity control of the compressor. So all these aspects lead to a certain amplitude and frequency spectrum of your pulsations. Well, we've noticed that pulsations propagate up and downstream in the pipe system, and they propagate at the speed of sound, c. The speed of sound is a quantity which is very important in pulsation control studies, and it depends on the gas composition and the temperature of the gas. Another important parameter is the acoustic wavelength, which is the length scale of the acoustic effects in the system, and it's a combination of the speed of sound and the frequency of the source. So the formula for the wavelength is this. In this table, I summarized a few of the features for 3 examples. For natural gas, which has a typical nominal molecular weight, for hydrogen, which is a very light gas with a low molecular weight, and also for CO2, which is a heavy gas with a high molecular weight. You immediately see the effect on the speed of sound, which is nominal for natural gas, it's high for hydrogen, and it's a low speed of sound for CO2. And that means that the wavelength for these 3 cases is also different. I give an example here for a double-acting compressor at 375 RPM running speed. So then typically the wave number for that frequency would be 32 meters for natural gas, 120 meters, so quite long for hydrogen, and quite shorter for the heavy gas CO2. So in general, you can see that the wavelength is typically much larger than the diameter of the pipe. And this is a good thing because this enables the use of simplified simulation methods. So 1D calculation tools are perfectly valid to study these effects. It also means that it's less favorable that pipe systems have very little damping. So because pulsations can propagate many wavelengths before they are really being disturbed, that means that in pipe systems, the damping is low. And as a consequence, pulsations can propagate to large distances away from the source and still cause problems. So that's the important takeaway, that even if you are far away from the compressor, 100 meters, for a hydrogen system is still pretty close to the source. So you can expect at large distances, you should be careful that you mitigate all the potential problems. This is about pulsations which propagate undisturbed, but in reality, of course, a pipe system has obstacles, and at each obstacle, the acoustic waves are reflected or partly transmitted. You can see that in this animation, or it's not an animation, but in this illustration here. An acoustic wave is approaching a diameter transition, and upon this transition, part of the wave is reflected and part of the wave is transmitted. And of course, the ratio between those depends on the area ratio of the transition. And upon reflection, what you will see is a shift in amplitude and a shift in phase in general. And examples of these obstacles, so the reflection points in pipe systems, are a diameter transition or a large vessel, but also a closed side branch can be a point of reflection. And in general, any discontinuity in temperature or density or the speed of sound will also reflect pulsations. So a cooler, for example, is another example where you will have reflections of your pulsations. And these reflections cause an interplay of up and downstream traveling waves in the system, which can at some locations have a constructive interference, they add up, or at some other locations they will have a destructive interference, so they will cancel or partly cancel. And this effect is called acoustic resonance. And it means that at certain frequencies, the system is very strongly responding to the source. It's illustrated here in this picture. So at the frequency of the resonance, you can have a very strong amplification, and the actual amplification depends on the damping. So the acoustic damping in the system determines how large the amplification will be in resonance conditions. In general, we note the positions where the pulsation amplitude is minimal with a note, and locations in the system where the pulsation amplitude is maximum, we call it an antinode. And here you see an example of a resonance, which happens here between a discharge pulsation damper and a large header. At certain frequencies, exactly half a wavelength fits into this length, in this organ pipe, if you like. So for this example, you will have minimal pressure pulsations at the node and the node, and you have maximum pressure pulsations at the antinode in the middle. So this is a nice example of a half lambda standing wave resonance, which is the most common type of resonance you observe in systems. Also, other resonances can occur, like the Helmholtz resonator, depending on the properties of the system and the speed of sound. So we have talked now about pulsations in general. Usually we talk about pressure pulsations, so fluctuating pressure. We will see later that for the flow meters, the fluctuating flow is more relevant, and there is a relation between pressure and velocity fluctuations. The acoustic pressure and the acoustic velocity are related by the conservation equations in principle. And important to note that the difference is that the locations where the nodes and the antinodes occur are in general different for pressure and flow pulsations. For example, if you have a closed open pipe configuration, like a side branch, you will see that the pressure pulsation amplitude will be maximum at the closed end, and the pressure amplitude at the open end will be minimal, 0. But the velocity fluctuation is exactly the opposite. The velocity fluctuation will be 0 at the closed end and will be maximum at the open end. So keep in mind that this standing wave pattern for pressure is really different than the standing wave pattern for velocity. And what's also important to note that even if you have low acceptable pressure pulsation levels, that does not necessarily mean that also the velocity pulsations are low compared to the mean value. For example, a pressure amplitude of 1%, which is a typical value in pipe systems, typically the target is around 1% of the ambient pressure, the static process pressure, I mean here. The velocity fluctuation can be much larger compared to the mean gas velocity. That can be easily 10% or even 100% or even larger, depending on the mean gas velocity. So beware that even if you have acceptable pressure pulsations, the flow pulsations, especially the relative flow pulsations, can still be large. Focusing a bit more on the flow pulsation effects, we have seen that the key parameter is the relative flow pulsation, which is the fluctuating flow divided by the mean static flow. And if you consider a flow fluctuation, in this case, as a function of time, you see the fluctuating flow with the mean flow, the dashed blue line. If you now have exactly the same amplitude of fluctuation, but at a lower mean flow, the red curve, you will see that the ratio between the fluctuation and the mean flow is much higher in case of the red curve. And what is more important, the red curve even has small time intervals when the flow reverses. So you have to have a short negative backflow, and then the flow is positive again. And these occurrences of instantaneous negative backflow we call flow reversal. And you can imagine that this effect can be quite severe. For example, on non-return valves, you can have the effect that the non-return valve tries to close and open upon this flow reversal. So that could be a bad thing. And also for flow meters, this is something to be aware of. So this scenario can be found, for example, in depleting gas fields, when the flow of the gas is slowly going down over the years. Then you can end up in a situation that you reach these conditions. But it can also happen in systems with a very large turn-down ratio. So if you run a system at 10% of its capacity or even lower, you can have this. And also it's noteworthy that in these cases, when you have a very low flow, also your pulsation control methods may be less effective. For example, restriction orifice plates will be effective at large flow because they give a significant pressure loss. But at very low flow, they will not give a pressure loss and they will not be very effective to dampen pulsations. So the combination of these two effects, low mean flow and high pulsating flow, that's the bad situation you try to avoid as much as possible. And a side note on this is that in future systems, for example, the next generation green hydrogen production systems, this may be exactly happening because these systems, they are supposed to operate at a very large turn-down ratio. They're very volatile systems. And you remember hydrogen, large wavelengths, little damping. So in these systems, the pulsations can propagate really far from the source. Moreover, you have a limited effect of volumes in the system. So the buffering of the system is also due to the high speed of sound low. And finally, in green hydrogen systems, the hydrogen flow is really also the economic driver. So the metering requirements are very strict. You really need to accurately measure the hydrogen flow in these systems because that's the primary fiscal or economical product we are talking about. So for the green hydrogen production systems, we think these effects will be even more pronounced and relevant. Well, what can be the effect of pulsations? Pressure pulsations, that's a quite common consequence. Pressure pulsation leads to a shaking force of the piping, so to vibrations, possibly fatigue failure. You see an example here. Another example could be damage to compressor valves. These are quite of course, severe, but also quite obvious negative consequences. For flow pulsations, that's slightly different. For non-return valves, if they start hammering in pulsating flow, that's something you obviously notice. That can be noisy, it can even lead to high vibrations or pulsations, but the impact on flow meters is not easily observed. If you have a high flow pulsation on the flow meter, you don't see a vibration, and even in the reading, it may be wrong, but you do not immediately notice that something is wrong. So that's why I call it a bit a thief in the night. It's a bit tricky, it's difficult to identify in the field if something is wrong. And the error can be small but systematic, and how to detect that. So that's why we create awareness for this effect, because it should be studied during the design. What can you do about it? Well, some of the conventional techniques, of course, also help to reduce flow pulsations. A good pulsation damper design is the first step. That can be a simple damper, it can be a damper with internals and choke tubes. So there are all kinds of techniques available to optimize the pulsation damper as much as possible. Restriction orifice plates are also, I would say, used in every compressor system, and the purpose of orifice plates is to bring down the effect of acoustic resonance. So the acoustic resonance effect is suppressed by the orifice plate. And in systems with a very large turn-down ratio, possibly you need an adaptive technique for that. So not a fixed orifice plate, but maybe a variable orifice plate. That could be an interesting technique also for future use. Modifications to the piping is something you try to avoid as much as possible, but sometimes it's really needed. And of course, adequate pipe supporting helps to reduce the risk on high vibrations. It will never be a solution for flow pulsations, because a pipe support will not mitigate the flow and the pulsating flow itself. What you can do for flow pulsations and optimization of the flow meter location. So during the design, you can choose optimal locations and avoid suboptimal locations. And in the standard, we gave a few examples of that. So a pulsation study can help to determine optimal locations for flow meters. And finally, but that's more the domain of the vendors of the flow meters, you can use advanced technology or signal processing within the flow meter to minimize the effect of pulsations. So summarizing the disturbing effects on flow meters, it's not only about pulsations. Another disturbing mechanism which is really relevant is non-uniform flow. And many of the flow meters will suffer if the flow is not uniform and not smooth and settled. So this is something which leads to typical guidelines that you should not put a flow meter very close to an elbow or a pair of elbows. A typical example of such a flow disturbance is a double elbow, because if you have a double elbow, then here behind the second elbow there will be a swirling flow, and that can disturb your flow meter reading. We talked a lot about the low frequency pulsations. These are typically the disturbing effects which are caused by positive displacement machinery like piston compressors. Even in the absence of piston compressors, there can be low frequency pulsation sources, for example, flow-induced pulsation effects. In a combination with a piston compressor, you will hardly see this, but in systems without compressors, still there can be other mechanisms which cause low frequency pulsations, and they will have exactly the same effect on flow meters as the pulsation of a piston compressor. High frequency broadband noise is typically a disturbing source which is generated by pressure let-down devices. So for example, a choke valve. When you have such a situation, you can expect very intense high frequency broadband noise, which can cause fatigue, rapid fatigue, but it can also disturb flow meters. For example, ultrasonic flow meters may be disturbed by this high frequency broadband noise. And finally, mechanical pipe vibrations, which can be caused by pulsations or by mechanical excitation of the machine itself. Also, the vibrations can disturb certain flow meters. For example, the Coriolis flow meter, it should not be exposed to excessive vibration because it may have trouble dealing with that. So several of these mechanisms can be observed. For example, if you have a high vibration and you have a wrong reading of your flow meter, it does not carry flow but still gives a reading nevertheless, that is typically effect you can expect in case of excessive vibrations. So these are the ingredients for the guideline, and we structured the guideline in a typical way. Typically for each type of flow meter, we have a separate chapter dedicated to the relevant flow disturbance mechanisms, so the mechanisms which can lead to a systematic error on the meter. And we also add, of course, references where possible to more detailed guidelines on the equipment to make sure you have background reading material. So this is the point to hand over to Andre, and he will be talking about the actual effects on the flow meters.
Okay, good afternoon, everybody, and it is a pleasure for me to guide you to the second part of this webinar. I will first start with the allowable flow meter error. Later on, I will give you an equation how you can calculate the flow meter error. But then the question is it acceptable or not? So there are two guidelines, the API 618 and the API 688. They give a flow meter error. That is for non-custody transfer applications 1%, and for custody transfer or physical metering applications, it's a factor of 8 lower. The difference between the API 618 and 688 is that 618 only states these flow meter errors, but the API 688 also gives some general information, which is also included in the guideline. The API guidelines or standards do not discriminate between the different types of flow meters, and it does not provide the calculation method to compute the flow meter error. The criterion for flow meter errors is much more restrictive than the pressure pulsations limit as used for structural integrity purposes. Another guideline is the ISO technical requirement 3313, and that states that the flow meter error is acceptable if the velocity pulsations are small compared to the time mean velocity. And that standard that uses so-called threshold value instead of an error. The equation for the threshold value is given here. That is the ratio between the root mean square value of the velocity pulsations divided by the time mean flow velocity. And the root mean square, perhaps you know it, but the root mean square is the square root of the mean time value over time. This ISO standard or technical requirement has a table with the different threshold values for different type of flow meters. You see that there are 5 flow meters and they only give the threshold value for 3 meters. And that has to do with the fact that it is not given for the Coriolis and the ultrasonic meter, because the flow meter error for those 2 meters are not dictated by the so-called velocity pulsations. It is said already, but the bias often specify unnecessary strict pulsation levels for a large part of the system when a flow meter is installed, and that is most of the time not necessary and quite costly. The first meter which I will discuss is a so-called differential pressure or delta P flow meter. The working principle is given in the left-hand side picture. So you have the pipe here, you have a restriction element, and most of the times the most applied restriction elements are the orifice plates, of which you see an example here. There's a plate with a hole, but also the Venturi nozzle or a flow nozzle can be used, which have some advantages. The pressure over this element is measured via the so-called gauge lines, and the signal will be processed further in the flow transmitter. The flow is measured by measuring the pressure loss, and the pressure loss is related to the velocity squared. So if you take the square root, you can calculate the mean time velocity. I will give now an overview of the possible flow meter errors. The first is a so-called square root error. What shall be measured is as follows. The first step is that you measure the pressure difference over the orifice plate. You take the square root, and then you take the time mean average value of the square root of the delta P. However, if you have a slow meter, what is measured then for that meter is this delta P is measured. That's still correct. But then it will measure it will dictate the time mean value of the delta P, and after that the square root of that will be taken. And that's exactly what causes the so-called square root error, because the two things are not the same. So you can calculate that the square root error is a function of the root mean square value of the velocity pulsations and the time mean velocity. This is, by the way, the only equation with which you can calculate the flow meter error, and that is for the delta P meter. The square root error is always positive, which means that a too high value is measured, and if you pay for the gas, of course you pay too much. And you shall also be aware of the fact that if the compressor load or the process conditions change, then also the error changes because the velocity pulsations will change. The velocity pulsations are very difficult to measure in the field and can only be determined with a detailed 618 pulsation analysis. So if you like to determine the square root error, you really need to do a pulsation analysis. The second error is the so-called gauge line error, and the pressure signals may be distorted by the length and also by the diameter change of these gauge lines. It is also possible that the so-called acoustic resonance, and then most of the time a quarter lambda or even a 3/4 lambda resonance can occur in the gauge line. You see that on this picture. You have the main line here. This is the gauge line. You have the flow transmitter here. And what you see is the amplitude of the pressure pulsations in case of a resonance. And you see that it is highest at the flow transmitter. So the recommendation for these gauge lines is, for that reason, you shall keep it as short as possible, such that the acoustic frequency of the gauge line is minimum 2 times the maximum frequency of the pulsations. You shall apply constant diameter tubing, fittings and manifold, and also the volume in the transmitter, the flow transmitter itself, shall be as small as possible. Errors can also be caused by the flow disturbance effect. Leonard has already told that, and they are difficult to quantify. So the flow shall be swirl-free, fully developed pipe flow, and the conditions meeting this requirement are specified in the ISO 5167 Part 1 and 2. And they can be minimized for all type of flow meters which are discussed and given in the guideline by installation of flow conditioners and flow straighteners, of which you see an example here on the right-hand side, and by placing the flow meter far enough from the obstructions bands T and reducers. The errors caused by the so-called low frequency pulsations, that is in general smaller than 200 Hz, can be as follows. Most applied effective measure is the installation of acoustic damping by means of an orifice plate, and the orifice plate shall be located where you have the maximum flow velocity pulsations, at so-called antinodes, and that is in the inlet or outlet, for instance, of volumes. You shall keep in mind that if you reduce the flow by unloading the compressor, for instance, it will lead to a smaller pressure drop, and that can result in larger flow meter error, even when the pressure pulsations are acceptable. Leonard also already explained it in his presentation. You can have an optimum location of the flow meter, and the flow meter shall be installed at locations with minimum velocity pulsations, the so-called nodes. And you see an example here. You see the velocity pulsation amplitude for a standing wave between 2 hard boundary conditions. Here it is maximum, and here at this node is the location where the meter shall be located. And flow meters shall not be located close to locations with flow disturbances. The next mitigation measure is that you can detune acoustic resonances, and that can be done, for instance, by shortening or lengthening pipe system, etc. It is also possible to acoustically separate the flow meter from the pulsation source, the compressor, for instance, by the installation of a large volume. It is also possible that you increase the header, and of course you can also choose a combination. Here are some rules given, 5 to 10 times the pulsation damper volume if you assume, or if you install a large volume, and the diameter shall be minimum 4 times the diameter of the connected pipe. And as being said already, you can install flow meter far enough from the compressor, and that shall be minimum 5 to 10 times the wavelength at the lowest compressor speed. You shall keep in mind that volumes, increased header diameters, and distances between compressor and flow meter need to be much larger for the higher speed of sound gases, for instance, for hydrogen. And I've given an example here on the right-hand side a compressor with a speed of 300 RPM, speed of sound 1200, and for 5 times the wavelength, you have already a length of 600 meters, which is quite long. If all the measures are not effective or are not feasible, then you can decide if you like to increase the damper volume or to apply a so-called acoustic filter. However, that is a very costly modification, and it is also challenging for a gas with high speed of sound, for instance for the hydrogen again, due to a lower acoustic effectiveness of the volume, which is related to the volume divided by the speed of sound squared. And of course, you can install a flow meter which is less sensitive for pulsations, and later on I will show you an example of that. Reducing flow meters, that means reducing velocity pulsations, can be much more challenging and also in general at much higher cost than reducing the pressure pulsations according to the API 618. The second meter is the Coriolis or mass flow meter. The working principle is given in the left-hand side picture. You have a pipe, and if there is a gas flowing through that pipe, if that pipe is rotated, you get a so-called Coriolis acceleration, resulting in a Coriolis force, which is perpendicular to the pipe. The pipe is in general a U-tube, and the pipe will be excited with a so-called excitation or drive frequency at the first mode shape of the U-pipe, and that can be done here with a magnet or at other locations. If a flow is flowing through that pipe, you get the Coriolis forces, and they are opposite for both legs, and that result in a twisting of that pipe, and that will cause a frequency which is called the Coriolis frequency, and also a Coriolis mode shape. Due to the fact that it is twisting, you have a twist angle, and that means that you also have a phase shift or phase angle between the two legs. So if you've measured the both thickness here, you can see that the mass flow rate is proportional to the time delay of that phase shift. Possible flow meter errors. The first is a so-called what we call the direct excitation, and that is an excitation by pulsation-induced shaking forces. If you look to the right-hand side picture, this is a U-tube. These red arrows indicate the pulsation-induced shaking forces, which are always in the axial direction of the pipe. So you have 3 forces here with a phase shift, and also a different amplitude is possible. This is the case if there is an acoustic resonance with a pulsation frequency Fp which coincides with the so-called drive frequency F1. However, the tube is in general small, the length of the tube, compared to the wavelengths, and that means that the pulsation-induced forces are in general low, and also the flow meter error will probably small for that meters. There is also a so-called indirect excitation of a Coriolis tube if the pulsation frequencies Fp coincide with the drive frequency F1, and the effect is that you get tube vibrations with a frequency of Fp plus F1, so the pulsation frequency plus the excitation frequency, and also the pulsation frequency minus the excitation frequency. And in general, the effect is strongest for Fp plus F1 when the frequency of the pulsation coincides with the Coriolis frequency F2. Another important flow can be an excitation by external vibrations. External vibrations can be caused by the main process pipe in which a flow meter is installed, and if that happens with a frequency very close or a coincidence with the excitation frequency of the U-tube, then you can imagine that it will have an effect on the flow meter. And it can also occur that if there are equipment in vicinity of the flow meter, for instance here, you have here a structure, for instance a pump is located here. Imagine that the flow meter is located here. You get structure-borne noise vibrations which will be transferred to that meter and will have an influence of the flow meter error. The external vibrations with the Coriolis frequency F2 will also produce a meter error, and that is most sensitive in the vertical direction of the pipe and around the axis. I hope you can see it, but it is around this axis. Absolute effects of all errors are very difficult to quantify, and there is not an equation for that. And the methods are given in the guidelines are able to judge if relative mitigation measures are effective or not. So the first is, because the error is driven by frequencies effect, the best way is to shift the excitation frequencies of the pulsations, and that is to try to avoid the coincidence of the frequency of the dominant pulsation forces, both with the drive frequency and Coriolis frequency. And a separation margin of minimum plus or minus 20% is a very good criterion to get away or to stay away from the excitation in the Coriolis frequency. The shifting can, for instance, be achieved by changing the pipe lengths, and it shall also be mentioned that if you have a variable speed compressor, the chance is very high that you can excite more than one acoustic resonances, so you shall be careful with that. The reducing of pulsation amplitudes at the meter location, it has been said already, by acoustic filter, orifice plates, etc., and also by relocating the flow meter. The mechanical vibrations, you shall try to avoid the coincidence of the dominant mechanical vibration excitation frequency, FV, with the drive frequency and the Coriolis frequency. And again, you shall have a separation margin of plus or minus 20%. And that can be achieved in a very easy way by the installation of very robust pipe support, which supports the pipe in which the flow meter is mounted. And you see here the brace, which is also very, very effective. And again, the shifting can also be challenging for variable speed compressors. And due to the fact that you don't know what acceptable is, you shall discuss with the customer what the acceptable vibration levels at the meter shall be, which is not an easy task, by the way. The last meter which I shall discuss is the so-called ultrasonic meter that measures the flow velocity with ultrasonic waves. You see the meter here. You have a so-called upstream transducer which sends out an ultrasonic wave to the other transducer, and after that the transducer will send back also an ultrasonic wave. What you see here is the equation for the so-called transit time, so the time from A to B and the time from B to A. The flow is flowing in that direction to the right-hand side, and these are the equations. And from these equations you can determine the time mean velocity, which is a function of the length between the receivers or the transducers, the angle here, and also about the transit times from A to B and from B to A. An advantage of this meter is that you can also calculate or measure easily the speed of sound, which is given by this equation. Summary of flow meter errors. The flow disturbances, they highly affect the performance of the flow meters, and single path ultrasonic meters are more sensitive than multipath ultrasonic meters. Pressure pulsations, and especially when you have a high amplitude pressure pulsations, it can change the profile. Looking to the right hand side picture, this is the picture of a flow profile at one location for at different times. This is, for instance, a pressure pulsation amplitude. When you have no pulsation, you can see that you have a normal flow pattern. However, if you have a very high pulsation amplitude, the flow pattern can be distorted, and it can even be reversed, as being mentioned already by Leonard. And you can imagine that that velocity profile may not be correctly sampled. However, an advantage of ultrasonic meters is that they can adjust it for this phenomena. It can also distort the ultrasonic pulses, which is sent out from one transducer to another transducer. And that is very important when you have a so-called high frequency broadband noise, when the meter is, for instance, installed downstream of a pressure let down device. However, that is not what is often occurring at reciprocating compressor systems. Aliasing, so that is overlapping of frequency components when the sampling rate is below a certain frequency, the Nyquist frequency. The Nyquist frequency shall be minimum 2 times the maximum frequency which you like to see in a signal, and that results in distortion or artifacts when the signal is reconstructed. So on the right hand side, this is the normal, let's say, shape. If you have an oversampled signal, then you see that you get the exact shape back. However, if you have an undersampled signal, you see that there is an overlapping, and that will lead to an error. And that happens in pulsation flow when the sampling frequency is often between 5 to 100 Hertz, is lower than the maximum frequency of the velocity pulsations. Mechanical vibrations, the meter itself is not sensitive to vibrations. However, the electronics may be damaged if you have too high vibrations. Again, as also for the Coriolis meters, the ultrasonic meters, the errors cannot yet be predicted and vary by the type and brand of the ultrasonic meter. And also relative measures are given to minimize the flow meter. So again, the flow disturbances, you have already seen that mitigation measure. You shall keep in mind that the aliasing is correct, and you shall discuss it with the flow meter manufacturer. External vibrations, again, installation of robust pipe support, avoid that the electronics will be damaged. If you are in the selection process of the flow meter, for instance in a feed study, then the question is which flow meter shall be taken to minimize the flow meter error. This table gives is an overview of the different flow disturbances effect for different type of flow meters, and green means that it is less sensitive, and red means that they are high sensitive to pulsation and vibration flow meter errors. That is, I will conclude now with the conclusions. So the pulsation flow causes flow meter errors, which may be systematic and significant. The disturbing effect of flow meters are not easily to be identified in the field. In systems with intrinsic pulsation effect, for instance, positive displacement machinery, the impact of flow meter accuracy shall be carefully addressed during the design. Buyers often specify an unnecessary strict pressure pulsation level for a large part of the system when a flow meter is installed, which is necessary, and that in general leads to very costly adjustments. Absolute effects of errors are difficult to quantify, except for the delta P meter, and methods are given in the guidelines to judge if relative mitigation measures are effective. Reducing flow pulsations and subsequent flow meter errors can be more challenging than controlling pressure pulsations, as used for pipe integrity purposes. In green, hydrogen production system, already mentioned by Leonard van Lier, increased awareness of pulsation effects on flow meters is strongly advised. And a solution may be adaptive pulsation control techniques, which may be considered, and especially it's the case for the large turn-down requirement. And this EFRC guideline is recommended to use during the selection of a flow meter in an early stage of the project to avoid severe consequences. So now I will give the word to Tim again. He will summarize the webinar, and then after that, the floor is open for questions and answers.
Yes. Yeah, thank you very much, Leonard and Andre, for this very comprehensive overview about the flow meter errors and what we can do to avoid them. I think this is a very useful tool. We see it with this guideline. We can have an early check if we need to do something, or if our meter may be prone to pulsations, and with what kind of mitigations we can take. So everyone here, I highly recommend you to go to www.recip.org and download these guidelines. And please also check all the other standards we have there and all the other guidelines we have there, because they are quite useful for the reciprocating compressor systems. Yeah, now it's time for questions, as already mentioned. Yeah, please, if you have any question, put them in the chat. We have now one from Stephen. So I will just read it out for you guys, and maybe you can answer that. So Stephen has a client recipe compressor supply being challenged by the general contractor on flow based on a single ultrasonic flow meter on the discharge header. Now it moved on my screen. Sorry, I need to scroll. Discharge header. There are two compressors, each producing. With discharge pressure varying, can an ultrasonic flow meter cover this range accurately?
That's the question?
That's the question, yes.
Yeah. I think the best answer is that you shall contact your or the OEM of the flow meter, because that can strongly depend, I think, on the type and manufacturer of the flow meter. So I think it is difficult to give a general rule on that.
You need to first agree on the target. So what kind of pulsation amplitudes are still acceptable to have acceptable accuracy. And if that target is available, then you can use, for example, a simulation model to see if you meet these targets, to demonstrate that you meet these requirements. And if not, you can use the model to optimize the system, for example. So check how much extra volume you would need between your compressor and the flow meter to reach an acceptable limit. So that's indeed depending on the target. And you can use simulation tools to quantify the effects and make sure that you optimize the system accordingly.
Yeah, what's also indicated already is that, I don't know if that is already applicable for most OEMs of these meters, but they can be adjusted for different flow meter errors as being explained. And I think nowadays, I'm not quite sure, but if already artificial intelligence is used, there is a flow meter manufacturer in Germany, which has a new type of flow meter with a lot of ANI in it. And I can imagine that for these type of errors, they can be adjusted in such a way that you get the minimum error. I think that is also one of the advantages of the ultrasonic meter. I hope that it is an answer to your question.
Yeah. Thank you very much for the clarification. Yeah, let's go to the next question. This is from Thibaut from Howden, and it's about screw compressors. He's asking if you can please share some constraint and tips that came to your mind when looking at testbed applications where compressors of different sizes and running speeds need to be tested. Or for example, we use a testbed to run performance tests across the operating envelope of the compressor.
Yeah, I think in screw compressors also these are pulsating machines, but they're different from piston compressors in general, that the frequency of the source is usually much higher. The running speeds are higher. And another difference is that on screw compressor systems, the inlet pulsations at the suction side are generally lower than on the discharge side. So if you have strong pulsation effects in a screw compressor, it's usually at the outlet. So that could be at least maybe a bit of a no-brainer, but if you have the option to place the flow meter at the inlet, I think for a screw compressor that would be a better choice than at the outlet. For the rest, it depends on the frequency range. Well, the benefit of high frequencies is that if you have a much shorter wavelength, so the attenuation of the acoustic waves is also much more rapid. So if you put a sensor further downstream, maybe with a buffer volume in between, that would be the best location to place your flow meter. So yeah, these are a few ideas, quite simple, but if you want to quantify it more, you need a simulation model to quantify the effects and know the target to make sure that you design according to the target.
On the other side, I think if you have high frequency pulsation force, the wavelength is short, so the chance that you hit, let's say, maximum, also larger. That is the opposite.
The other side of the coin.
The other side of the. Yeah. So you shall be careful of that because of that, and I think the best way is to have an acoustic separation between the source, the compressor itself, and the meter. But I don't know if that is possible.
Yeah, for screw compressors, of course, the kind of dampers is slightly different, or is different in concept usually than for piston compressors. For piston compressors, you typically have empty vessels or vessels with internals, but for screw compressors, you typically see silencers, which are of a different layout, often also involving absorption techniques, so absorption material to suppress the effect of pulsation. So also for screw compressors, there are very robust solutions to dampen the pulsation effect, but they look different and they have different challenges than the dampers for a piston compressor.
Okay, yeah, thank you very much. So far, these are all the questions in the chat. Yeah, maybe someone is typing now and put some more. So we still have a couple of minutes time for more questions. If something comes into your mind at a later stage, don't hesitate to contact us. So we are always open for clarifying it. Yeah, let's wait maybe one more minute to see if one more question will come up.
Perhaps in the meantime, I can add a little history from the past. By the way, this guideline was being developed on your request, Tim, because perhaps you can explain it a little bit, what kind of problem you had during the design of a system with your large pulsation number which has to be installed.
That's a very good point. Yeah, so we came up with a request to design this guideline. So as always, you can always approach us for if you have any idea for guidelines, so we are always open to work on that. And this idea came from us because sometimes when you are designing reciprocating compressor system and you know that there's a flow meter maybe at the suction side of the compressor, the pressure pulsations are specified very, very low limit, for example 0.5% peak to peak, and this specification leads to very, very large pulsation dampeners. And then if you imagine you have a suction damper, this is always suction size is mostly on top of the compressor, so it's always an elevated damper, so you need to put a very big mass at a high elevation, and that leads of course to a low mechanical natural frequency of the system, and then the system is very prone to vibrations. And you're only doing this because it's specified for the flow meter. It doesn't have to do anything with the integrity of the system, only for the flow meter. And also, as we saw now with those presentations, also maybe especially for hydrogen, with these very small pressure pulsations, you can still have a huge flow pulsation and still have a huge error in your measurements. And therefore, we said it's better to develop a guideline and to find some other ways to handle this than just putting a very, very big damper on the compressor and maybe run in other problems.
Yes. Yeah, I can add, you mentioned already, as the hydrogen system, of course, the flows will be huge and much larger than for natural gas systems. And it is, I think, becoming more and more important to measure that in an accurate way, because I never made that calculation. But if you have a small error, you should calculate once what you have to pay for the flow meter error if that will occur, if there is a difference between the producer and the buyer of that gas. So it is worthwhile to spend money in the very early stage of your design to think about what can happen when you have a certain flow meter error.
Yeah, that's definitely true. So there are no more questions arise. As already said, please feel free to contact us. Please visit our website. So then we are over with the webinar. So Leonard and Andre, I thank you very much for giving us this detailed insights. Once we close it now, there will be a survey coming up. And I kindly ask all of you to take the time. It's just 2 minutes of your time to fill out the survey. So this helps us to improve. And also there's a question about ideas for further webinars. Please feel free to enter this. We are always, of course, interested. What's your topics and what can we do about it? Thank you very much for joining, everyone. Wish a nice day ahead, nice week ahead, and I hope to see you in one of our next webinars.
Or next year, the conference in Hamburg.
Or at the conference, exactly.
Yeah, that would also be nice.